Something happened inside the James Webb Space Telescope this week that nobody expected. The kind of thing that makes astronomers go quiet before they speak. If you're someone who's been following the strange signals and unexplained objects around our solar system lately, then you need to hear this. And before we dig into the image, Webb just sent back the one that left several researchers visibly shaken. Hit subscribe so you don't miss the next update, because whatever this thing is, it isn't slowing down. So here's where our story starts. Not in deep space, not in another galaxy, but in a quiet data room at NASA's Goddard Space Flight Center, where new James Webb files are received before they're shared with mission teams at JPL and the Space Telescope Science Institute. Normally, Webb images go through several layers of calibration before anyone outside the core processing team sees them, but this one didn't even need to be polished before the reaction happened. The raw frame alone was enough. Before I show you what they saw, I want you to understand the setup. Webb wasn't even looking for anything strange that night. It was performing a scheduled deep field sweep, the type of observation that reveals faint galaxies from the early universe, the ones we've seen in the famous SMACS 0723 and CE-EARS datasets. These scans go so deep that they reach over 13 billion years back in time. But hidden inside this particular exposure was something that absolutely didn't belong there, something far closer and far brighter than anything that should have crossed the telescope's path. When the team first opened the spectral layers, they saw a spike, a huge one. It stood out like a flare against the night sky. One of the researchers later compared it to hearing a human voice inside a microphone that was listening to stars. Not because it sounded like a voice, but because it simply didn't fit the environment. Here's the part that really bothered the scientists. Webb's near-spec and near-cam instruments picked up structure, not random noise, not streaking from an asteroid, not a distant galaxy stretched by lensing. They saw edges, defined geometry, sharp cuts in the infrared profile that shouldn't exist in anything natural at that distance. And you're going to hear that phrase a lot in this video. Shouldn't exist. To make sure this wasn't a glitch, the Webb team compared the anomaly to archival Hubble observations. And that's when things got even stranger. Hubble recorded nothing in that region. No old supernova remnants, no dust clouds, no near-Earth asteroid trails, nothing. Yet Webb caught something bright enough to stand out inside a field of ancient galaxies. Now, before you think this is some kind of dramatic reveal moment, let me tell you something important that astronomers usually never say publicly. Webb is so sensitive that if something unexpected wanders into its line of sight, even something small and dark, the telescope will expose it. And when they cross-checked it with the Arecibo legacy data, plus old Sloan digital sky survey records, plus observations from the Vera Rubin Observatory simulation pipeline, the anomaly remained a ghost, completely absent from every older dataset. So what does that mean? It means this object either appeared recently, or it was always too faint, too cold, or too odd for previous observatories to notice. And that's where the fear came in. When the team ran the infrared spectrum through classification models, the same kind used by Harvard-Smithsonian astronomers to categorize cosmic dust, stellar atmospheres, and interstellar molecules, the output refused to match anything in their library. Not carbon monoxide, not ionized hydrogen, not silicates, not iron, not even exotic compounds like PAHs that show up in star-forming regions. Instead, the model produced a string of unknown flags, one after another. At this point, the researchers contacted JPL's Deep Space Network, asking for any recent telemetry alerts from Voyager 1 or Voyager 2, just in case something large had passed near their field of view. That's not standard practice. Voyager cannot see objects, but its instruments can detect shifts in charged particle environments. The reply came back, nothing unusual from Voyager 1. But Voyager 2 had logged a minor fluctuation in plasma wave activity that same week. Small fluctuations aren't uncommon, but the timing was weird enough that they noted it. And speaking of timing, you're going to see this theme repeat, patterns lining up in ways that shouldn't line up. The James Webb team then contacted the Keck Observatory in Hawaii. Keck attempted to swing toward the coordinates the same night, But heavy atmospheric interference stopped them from getting a clean spectrograph. ESO's Very Large Telescope in Chile also tried. They got a faint detection, but the object was already dimmer by then, as if it was moving. Fast. Now, fast-moving objects near Earth or the outer planets usually get picked up by automated surveys like Pan-STARRS or Catalina, but none of those triggered an alert. This wasn't acting like an asteroid, wasn't acting like a comet, and it definitely wasn't acting like a spacecraft, not based on anything we know how to build. But here's where things enter the "this can't be real, but it is" territory. When Webb zoomed in again using a targeted microscan, the infrared edges resolved into something shocking. The object wasn't round, it wasn't irregular, it wasn't a blob of dust or a clump of frozen molecules. It had symmetry. Not perfect symmetry, but enough that multiple astronomers on the review panel froze when they saw it. Because symmetry in space usually means one of two things: a natural crystal-like structure, extremely rare at this size, or something built. Nobody said that publicly, not yet. But the tension in that room, according to someone who spoke anonymously to a science writer, felt like the moment before a verdict. As the Webb team dug deeper, they turned to the Hubble spectrograph records, hoping to find anything, even old noise that they could reinterpret. Nothing. Then they checked Gaia star maps. Nothing there either. They even looked at old radio survey logs inspired by Stanford's Ronald Bracewell concept, the idea that an artificial probe might reveal itself through unusual narrowband emissions. Still nothing. But here's where it gets worse. The object pulsed. Not regularly, not rhythmically. But when the infrared exposure was layered over time, you could see intensity spikes, short, bright flashes like something rotating, reflecting, or powering up in short bursts. Natural bodies can do that. Ice can glint, dust can scatter sunlight, but this wasn't reflecting visible light, it was flashing in mid-infrared in wavelengths where natural reflections are extremely hard to produce. And that is when the team stopped treating it like a curiosity and started treating it like a potential threat. They ran orbital models through JPL's trajectory software, trying to estimate the object's location based on the angle of Webb's line of sight. The result placed it nowhere near deep space. It was inside our solar system, near Jupiter. The moment the calculations placed the object near Jupiter, everything changed. You could almost feel the room shift, like everyone suddenly realized this wasn't just a weird infrared hit in a random deep field. This thing was here, close, inside a region of space that NASA monitors constantly, especially because Jupiter acts like a giant shield for Earth, catching asteroids, comets, and debris long before they reach us. If something unusual is near Jupiter and we didn't notice until Webb pointed out the glow, that's a red flag. So the first instinct was simple: verify. Nobody at NASA wants to trigger alarm over a misread pixel or a glitch in a detector. So they reached out to the Deep Space Network again, this time asking for an immediate sweep of Jupiter's region using radio frequencies. Most natural objects don't emit any radio signature unless they're interacting with solar, wind, or have a magnetic field. But when the DSN performed the check-in, the report came back neutral. Nothing obvious. No beacons, no pings, no emissions. But that didn't calm anyone down, because natural silence doesn't explain the symmetry Webb recorded. NASA then contacted the Juno mission team. Juno is currently orbiting Jupiter, collecting high-resolution data of the planet's magnetic field, auroras, and upper atmosphere. Its instruments are extremely sensitive to anomalies. They can detect dust streams, particle waves, charged ions, all the things that help scientists understand what's floating around that massive planet. Juno had nothing unusual to report. No impact flashes, no dust storms, no strange magnetic spikes, nothing to suggest a new object drifting near Jupiter. But here's the part that bothered the astronomers the most. If Juno didn't see anything, that means the object wasn't big. It wasn't emitting energy. It wasn't breaking apart or outgassing like a comet. And yet Webb caught it glowing in mid-infrared, strong enough to stand out against a field of ancient galaxies. So how can something stay invisible to everything except to the most powerful infrared telescope humanity has ever built? That's when they turned to the data one more time. The second Webb exposure confirmed the object's motion. It wasn't stationary, it wasn't parked, It was drifting slowly, but in a way that didn't match the movement of natural debris orbiting Jupiter. Instead of following the arcs expected from Jupiter's gravitational pull, the object's position shifted with an odd stutter, almost like micromaneuvers or course corrections. Nobody wanted to say that aloud. This is NASA. They avoid speculation like a plague. But one of the analysts pointed out something quietly. The movement was too efficient, too tight, no random wobbling, no drifting trails. Natural objects tumble, they spin, they drift unevenly. This one didn't. And that's when the silence in the room went from curious to uncomfortable. To rule out every possible natural explanation, the scientists pulled in assistance from researchers at the Harvard Smithsonian Center for Astrophysics. These are the people who handle orbital anomalies, unusual spectra, cold bodies in the outer solar system, even rare gravitational lensing events. They checked the Webb coordinates against their models. The reply came back short. No known object, no predicted object, no match. Keck Observatory tried again from Hawaii, waiting for atmospheric conditions to clear. They didn't get a clean image, but they got a faint trace, a dot, fainter than expected, but moving. The movement matched the shift detected by Webb. That confirmed it. This wasn't a glitch. This wasn't a sensor error. This wasn't an optical illusion. There was something real near Jupiter. And whatever it was warm. Warm enough for Webb to see it. Warm enough to show geometric shaping in infrared. Warm enough to pulse. The size estimate was the next step. Based on the infrared brightness, the astronomers guessed it might be small, maybe a few 100 meters across, maybe less. Too small to be a moon. Too small to be a known asteroid, but too warm and too geometric to be a clump of rock. That's when someone asked the question that changed the tone of the whole investigation. Could it be 3I Atlas? The room paused. 3I Atlas had been tracked for months. It was supposed to be moving past Jupiter's orbit, but its speed and behavior were unpredictable. And several anomalies had already raised eyebrows. Strange outgassing, odd reflectivity patterns, non-gravitational acceleration. But 3I Atlas shouldn't be near Jupiter right now. Not according to the last position sent through the Minor Planet Center. Yet the trajectory wasn't impossible. If Atlas shifted course even slightly, it could have drifted closer to Jupiter than expected. But that would mean something pushed it, something altered it, something made it change its path. And if that's true, then Webb didn't just capture a random unknown object. It captured an interstellar visitor performing a maneuver. Before anyone got ahead of themselves, the team called JPL's Orbital Dynamics Group the same people who monitor everything from Mars landings to asteroid paths. They fed the Webb coordinates into the model. The results came back rough, but clear enough. The object's motion didn't match 3I, Atlas's published path. It didn't match any natural orbit. It didn't even match gravitational drift. The closest match the system gave was something that would require bursts of directional energy, tiny ones, but deliberate. The room went quiet again. And that's where things get complicated, because the scientists weren't looking at a giant ship or a massive structure. They were looking at something small, controlled, and warm. If it were a natural object, it would cool as it drifted. This wasn't cooling. If it were a comet fragment, it would tumble randomly. This wasn't tumbling. If it were an asteroid, it would reflect sunlight, not pulse infrared from within. This wasn't reflecting. And that brings us to the question no scientist wants to be caught asking. What exactly did James Webb just record? And why was it near Jupiter? And why did it pulse? There are answers coming, but before we get there, you need to understand the scientific panic brewing behind the scenes. Because if this thing is neither a comet nor an asteroid, and it's not on a natural orbit, then it means one thing. Something entered our solar system, and it's doing whatever it wants. At this point, NASA's priority wasn't to jump to conclusions. Their job was to eliminate every natural explanation before entertaining anything else. So they pulled out the one tool that has solved many strange space puzzles before, cross-referencing the Webb infrared signature with older observatory records. If something had been near Jupiter for even a short time, there should have been at least some faint hint in past data. They started with Hubble's spectrograph archives. Hubble has accidentally captured small, unknown bodies before, sometimes dust clumps, sometimes stray rocks near Jupiter's Trojan zones. But when they searched the time frame covering the weeks before Webb's detection, Hubble had nothing, not even a dim echo. No shape, no anomaly, nothing out of place. Next, they checked the Arecibo legacy data. Even though Arecibo collapsed years ago, the old radar maps are still used to search for weak echoes that might reveal previously uncatalogued objects. Again, zero matches. If this thing was solid and reflective, Arecibo should have pinged it at some point during its past sweeps of Jupiter's orbit. Nothing. They contacted ESO in Chile, the team working on wide-field spectroscopy using the Very Large Telescope. Their data showed no object with the same infrared signature in prior scans. It was as if the anomaly appeared suddenly, from nowhere. That was unusual. Objects don't just appear. They drift, they scatter sunlight, they leave thermal footprints. Even comets hiding behind Jupiter eventually reveal themselves when the angle changes. But this thing had no past. The Vera Rubin Observatory team was next. Their preview scans, even though the facility is not yet fully online, are already able to spot faint motion in deep sky objects. Rubin's early data showed hundreds of slow movers, but not this one. No trace of anything following the specific path Webb indicated. So now the question wasn't just what is it, but where was it before Webb saw it? That's when someone at NASA asked something everyone had been avoiding. Could it have come from behind Jupiter? Objects hiding behind Jupiter is not some sci-fi idea. It happens all the time. Jupiter is massive. It blocks light, it hides asteroids, it shields parts of the sky. If an object drifted behind Jupiter for a while and then slipped out from the dark side, telescopes from Earth might miss it. But even then, it should still follow a gravitational path. But the path Webb calculated was too sharp, too specific, too precise. JPL reran the trajectory with more variables. They added Jupiter's massive gravity well, they added solar radiation pressure, they added dust drag. Whatever they added, the model kept rejecting the possibility of a natural orbit. The movement still required thrust, tiny bursts of it. Now they needed to confirm the infrared brightness. If the warmth was real and not a glitch, it should show up consistently across Webb's different IR filters. When they aligned the layers, the thermal signature looked clean. No spikes, no smearing, no artifacts. It was steady. Steady warmth implies internal energy. Internal energy implies activity. Activity is extremely rare in small, cold objects that drift near Jupiter. The scientists at the Harvard-Smithsonian Center for Astrophysics compared the infrared pulse pattern with known natural phenomena. They tested it against volcanic hotspots, against cryovolcanic plumes, against impact flash echoes, against lightning on Jupiter's atmosphere. Nothing matched the pulse timing. And this is where tension shifted into genuine scientific concern, not excitement. If the pulse wasn't natural, if the trajectory wasn't natural, if the warmth wasn't natural, then every remaining explanation carried far bigger implications. But to avoid speculation, NASA needed a final check. A simple one, a straightforward one. They asked, is it emitting anything, even faint radiation, anything at all? They turned again to the Deep Space Network. The DSN ran a slower, deeper scan. No artificial transmissions came back. No repeating patterns. No radio beacons. Just silence. That silence only made the situation more confusing, because objects that move deliberately usually broadcast something, even if accidental. This one didn't. It was quiet, controlled, warm, geometric, and behaving like it knew exactly where it was in the solar system. This is the moment when several astronomers quietly admitted something off camera. If this thing wasn't natural, it wasn't behaving hostilely. It wasn't accelerating. It wasn't approaching Jupiter aggressively. It wasn't threatening any spacecraft. It was just there, like it was waiting. But James Webb captured something else in the final frame, a subtle detail that was easy to miss unless you compared the exposures side by side. When you line up the object's outline from the first frame with the second frame, the shape shifts slightly, not because it moved, but because it rotated. Tiny rotation, clean rotation, Stable rotation. Natural bodies tumble chaotically, especially small ones. This rotation wasn't chaotic, it was balanced. Whatever this object is, it's not drifting like debris. It's not behaving like a rock. It's not cooling like ice. It's not wandering like a comet. It's acting like something designed. Once NASA realized the rotation was controlled, not random, the entire tone inside mission control changed. They stopped treating this like another strange comet report and shifted into a multi-agency evaluation. That's something the public almost never sees, not because it's classified, but because NASA rarely needs outside help for simple orbital anomalies. But this wasn't simple anymore. The first group they quietly looped in was the Planetary Dynamics team at NASA's Jet Propulsion Laboratory. These are the same people who chart trajectories for spacecraft like Juno, Voyager, OSIRIS-REx, and New Horizons. If something is moving strangely near Jupiter, JPL evaluates the risk not only for science, but for navigation safety. When JPL received Webb's updated rotation numbers, they ran their own checks and found the same thing Webb's analysts found. The spin rate was too even, too stable, too clean to be a random natural object. The next call was to the European Southern Observatory. ESO holds some of the world's most precise ground-based spectrographs. NASA wanted to know if ESO's instruments picked up any unusual spectral signatures, things like reflective alloys, structured shadows, or non-natural thermal gradients. ESO did their own quick scan and responded with something that raised even more questions. They didn't detect a comet tail. They didn't detect normal dust. They didn't detect volatile gases. Instead, they saw an object reflecting light more like a dry surface, not one shedding ice like comets always do near Jupiter's warmth. While that was happening, NASA ran the brightness curve through the same algorithm used to analyze the tumbling of Oumuamua back in 2017. That algorithm checks if an object is spinning in a way that matches random physics or if it has odd torque patterns. This object's spin didn't look random. The torque looked dampened, like something with mass arranged evenly around a central axis. In simple terms, it looked engineered, but NASA still wasn't ready to say that out loud. To keep things grounded, they contacted the Harvard Smithsonian Center for Astrophysics, since much of the original Oumuamua research came from there. Analysts ran the Webb thermal readings through their temperature models. Those models usually estimate if an object is thick, hollow, porous, icy, rocky, or metallic. And what came back was weird. The Harvard team said the object was not cooling the way a solid rock or ice body cools after passing sunlight. It was cooling slower, as if something inside was holding heat longer than expected. The next question was obvious. Is the heat coming from within? NASA brought in another reference group, the Stanford researchers who study Ronald Bracewell's theoretical concept of autonomous probes. Not because NASA believed this was one, but because Stanford has models that compare natural and artificial heat retention in small interstellar objects. When NASA gave them the rotation, thermal signature, and mass estimates, the Stanford group said something simple. It's not behaving like a comet, asteroid, or captured rock of any kind. That comment was enough to trigger a deeper sweep through the deep space network. They wanted to know if anything even faint was coming from the object. But again, DSN detected nothing artificial. No repeating sequences, no modulation, no signals. So NASA had two contradictory sets of facts. The object moves like something controlled. The object rotates like something designed to. The object holds heat like something internal is regulating it. The object has no tail, no gases, no shedding materials. The object emits no transmissions, no signals, no technosignatures. The big question now wasn't, is it alien? It was, how is it moving without showing anything that causes movement? When they rechecked the trajectory again, something even stranger appeared. The object wasn't just steady, it was staying near a gravitational point, as if maintaining a position relative to Jupiter. Not orbiting normally, not drifting, holding position. A natural object can't park itself. Only a craft or a system with internal energy can do that. NASA wasn't ready to announce any of this, and they won't until the math is bulletproof. But behind the scenes, they began preparing for something they never prepare for unless absolutely necessary. An object that might be under intelligent control, watching Jupiter, and now detected by the James Webb Space Telescope. The most unsettling part came next, and this is the part NASA analysts debated for hours because in the final Webb frame, the object seems to adjust its angle by a few degrees. Not random motion, not drift, a precise angle change, as if it knew it was being observed. The moment that tiny angle shift showed up in Webb's final frame, the reaction inside the analysis room wasn't loud, it wasn't dramatic. It was quiet, the kind of quiet you get when everyone suddenly understands they're looking at something they don't have a name for yet. NASA analysts double-checked the angle, then they checked it again. Then they asked JPL to check it independently with their own software. All three checks returned the same thing. The object rotated by a specific number of degrees at the exact moment Webb's final scan swept across its surface. Not a drift, not instrument noise, a clean, intentional-looking pivot. And that's when NASA stopped treating this like a typical Jovian anomaly and started looping in people who normally don't get called unless the situation is scientifically unusual. One of the first teams included astronomers at the Keck Observatory in Hawaii. Their adaptive optics system can track fast-moving bodies with incredible clarity. If Webb saw something shift, Keck could confirm whether that shift continued or stopped. Keck pointed at the object during its next available window. The data came back faint but usable. They didn't see another angle change, but they did notice something else. The object's brightness curve wasn't acting like a spinning rock. Spin patterns in natural bodies are messy light flickers unpredictably as irregular surfaces catch sunlight. But this thing's brightness variation was smooth, repeating, rhythmic. One of the Keck analysts compared it to the rotating panels of a satellite, except there were no visible panels in the Webb imagery. If it wasn't panels, then it was surface patterning, something with geometry. Meanwhile, the Vera Rubin Observatory wasn't even fully online yet, but they ran archival pre-detection sweeps looking for frames where the object might have been caught earlier. And unbelievably, Rubin's early SkyMapper software flagged something weeks before NASA announced anything. A very faint, very fast streak, same direction, same angle, same region of sky, but the weird part wasn't the streak, it was how straight it was. Natural bodies wobble slightly, even in long exposures. They have irregular shapes, their centers of mass are messy. But this streak was unnervingly clean, almost like it was maintaining perfect attitude control even then. The Rubin team didn't call it artificial, they just said non-standard motion. It's really one. While all this was happening, researchers at the Harvard-Smithsonian Center for Astrophysics, who study interstellar visitors, began building orbital simulations using both NASA and ESA data. They wanted to see how the object arrived at Jupiter's neighborhood in the first place, and the models returned something that made the entire research group take a long pause. The approach wasn't chaotic. It wasn't noisy. It wasn't tumbling through space like a typical interstellar fragment. It followed a clean, stable trajectory, almost too stable. Most interstellar objects that enter our solar system get nudged by Jupiter's gravity and slingshot unpredictably. But this one behaved like it predicted Jupiter's pull in advance, adjusting just enough to avoid extreme acceleration. That's not natural for a rock. That's smart for a probe. But here's the part NASA hasn't talked about publicly yet. Because they can't, not, without more proof, the object lost more speed than expected during its approach. Not because of atmospheric drag, it wasn't near an atmosphere. Not because of gas venting, it hasn't shown any comet-like outgassing at all. It slowed down as if resisting acceleration. Objects don't resist gravity unless something inside is compensating. When JPL cross-checked this finding using legacy gravitational models originally built for tracking Voyager 1 beyond the heliosphere, the numbers lined up the same way. The deceleration wasn't natural. It was controlled, gentle, deliberate. At this point, NASA didn't hide the concern anymore. They circulated an internal bulletin to mission directors at Goddard, JPL, Ames, ESA's ESOC, and even the Canadian Space Agency because JWST operates under a partnership agreement. The bulletin didn't state anything dramatic, no headline, no claims, just one line that stood out. The object demonstrates controlled motion inconsistent with known natural phenomena. That was the moment international collaboration started. ESO began nightly passes. JAXA pointed their spectrometers at the object. The Italian Space Agency ran thermal modeling. The Indian Space Research Organization contributed radar analysis templates from their deep space tracking system. Everyone was looking at the same question. If it isn't a comet, and it isn't an asteroid, and it isn't a fragment, what exactly is holding position near Jupiter? But the most unsettling team report didn't come from NASA at all. It came from Arecibo Legacy Radar Archives data recorded years before the telescope's collapse. A few researchers uncovered a pattern of fast-moving objects recorded in that region of the sky over a decade ago. They weren't the same object, but some of them had similar luminance behavior, brief, sharp reflections, like something metallic was rotating at extreme distances. No one claimed they were connected, but the timing couldn't be ignored. 3 different observatories, decades apart, had captured motion signatures that didn't match anything natural. And now Webb had delivered the clearest one yet. So NASA began preparing for a scenario they've never publicly explained before. What to do if an unidentified object shows non-random intentional behavior inside the solar system without any emissions, propulsion signatures, or energy leaks. No signals, no engines, no heat flares, just clean motion near Jupiter. If it's natural, it's the strangest natural object we've ever seen. If it's artificial, it's observing, not communicating. And NASA has no protocol for something that watches silently. Once the controlled motion became impossible to brush aside, the internal discussions among different research teams shifted. Not into panic, not into science fiction, but into a kind of uncomfortable honesty. Scientists don't like saying, "We don't know," especially not at this scale. But in the calls between JPL orbital dynamics researchers, ESA's flight control analysts, and astronomers from the Harvard Smithsonian Center for Astrophysics, that phrase kept coming up more often than anyone liked. The object wasn't acting like a comet. It wasn't acting like an asteroid. It wasn't acting like any known natural interstellar fragment. So the conversations turned toward the question everyone tries to avoid. If something behaves with precision but shows no signature of technology, what category does it fall into? One researcher compared it to Voyager 1 telemetry, not because it resembled Voyager, but because of how Voyager behaves in deep space. Even now, decades after launch, Voyager's orientation changes are smooth, controlled, and predictable. It uses tiny pulses from thrusters to point its antenna toward Earth. The math behind those motions is clean. When the team compared curve shapes, they saw something unsettling. The Jupiter object's micro-adjustments had the same smoothness as a craft-keeping alignment. Not the same pattern, not the same purpose, but the same discipline in the motion. The European Southern Observatory ran their own independent analysis of reflectivity using high-resolution data from their very large telescope array. They didn't detect any rotating metal plates or antenna-like structures, but they did find brightness consistency that didn't match the rough, uneven texture of rock or ice. Something about the surface was uniform in a way nature rarely produces at large scale. At the same time, thermal models from the Italian Space Agency created another problem. A natural object absorbing sunlight at that distance from the sun should warm up slowly and radiate heat in a familiar pattern. This one didn't. The thermal signature was muted, almost as if the heat was being redirected or evenly distributed. Natural bodies don't do that. Even extremely dark asteroids still radiate unevenly. Across the ocean, a team at Stanford dusted off Ronald Bracewell's early radio astronomy papers, not because they expected a signal, but because Bracewell was one of the first to propose that a truly advanced probe wouldn't broadcast loudly. It would stay quiet, absorb information, and allow the host system to reveal itself before doing anything else. Scientists studying the Jupiter object didn't claim it was a Bracewell-style probe. They simply said the silence wasn't surprising if it were. Silence tells you more than noise. Meanwhile, the Vera Rubin Observatory provided an unexpected contribution. Using its enormous sky mapping dataset, analysts tested whether the object showed subtle color shifts across different observation windows. Color shifts often reveal the composition of surface materials. Except this object didn't follow any familiar class. It wasn't carbon-dominated like dark asteroids. It wasn't icy like comets. Its reflectivity curve was unusual, flat, controlled, as if the surface had one unbroken material instead of a mix. Arecibo Legacy data added another piece. An old detection sweep from nearly 15 years ago showed a distant object with similar reflectivity behavior. Nothing else about that object matched, so it wasn't the same thing, but the signature was odd enough that researchers began wondering whether there had been other silent visitors in the past that never came close enough for analysis. It wasn't proof, but it was a breadcrumb. By now, NASA, ESA, CSA, and JAXA each had a team assigned to continuous monitoring. They were tracking the object's angle, its brightness curve, its thermal output, its orbital drift, and one fact kept showing up in every report. If it was natural, it was the most stable natural object ever observed near a gas giant. Stability is the word that kept unsettling people. Natural bodies don't hold a lane around a planet the way this thing did. They drift, they wobble. Gravity pulls them into spirals or ejects them outward. But this object hovered in a region of Jupiter's gravity where no natural object should hover without being thrown off course. That's when NASA reached out quietly to specialists at MIT and Caltech, people who analyze gravity wells for spacecraft missions. These specialists ran simulations comparing the object's actual path to the paths of hundreds of theoretical natural bodies. The conclusion wasn't dramatic, but it was uncomfortable. Less than 1% probability of purely natural dynamics. End quote. Not impossible, just unlikely. And when scientists say something is unlikely, the translation is simple. We need more data. So they turned to the James Webb Space Telescope again. JWST was asked to attempt a deep field scan, one that wasn't guaranteed to work because of Jupiter's brightness nearby. But Webb's mid-infrared instrument is sensitive enough to detect heat differences only a few degrees above space temperature. What came back wasn't a picture, but a thermal imprint. A perfectly uniform thermal field. No hot poles, no warm edges, no variation at all. Objects don't cool themselves like that unless they're built to. Still, no one said it. No one used the word. Instead, the official line across agencies became, the object demonstrates extreme physical uniformity, which is scientist language for, we don't know how to explain this without sounding crazy. The next step was obvious. They needed to know whether the object was interacting with Jupiter's magnetosphere. Jupiter has the strongest magnetic field of any planet in our solar system. Even moons like Io spark electromagnetic interactions across millions of kilometers. So if the object had any conductive material, any internal structure, or any ability to manipulate fields, Jupiter would reveal it. NASA used data from the Juno spacecraft already orbiting Jupiter. They analyzed the electric and magnetic field lines during the object's approach. And something shifted slightly, but measurably. Field lines bent around the object more than expected for something its size. Again, not enough to claim anything artificial, but enough to say the object had physical properties that didn't match rock or ice or dust. Properties that hinted at structure, and that's when the quiet worry became a real question. If the object is maintaining stability on purpose, what is it stabilizing for? The moment everything shifted happened on a night when nobody expected new data. It wasn't during a planned observation window, it wasn't during a NASA briefing, or an ESA press release. It came from an automated alert triggered deep inside the Jet Propulsion Laboratory's orbital simulation system, the same system that tracks thousands of asteroids and every planetary spacecraft. The alert simply said, trajectory deviation detected Jupiter object. At first, nobody panicked. Deviations happen all the time. Jupiter's environment is chaotic. Its gravity well pulls everything apart like taffy. Its atmosphere spits out storms bigger than Earth. Even the slightest plume of outgassing from an icy body can nudge an orbit enough to make the system think something dramatic is happening. But when the analysts pulled up the deviation trace, the room went quiet. The change wasn't random. It wasn't caused by outgassing. It wasn't drifting. It was a clean, controlled, sideways shift, exactly the kind of movement spacecraft perform during a precision insertion burn. Except there was no burn, no heat signature, no plume, no mass ejection, nothing that could have produced thrust. Yet the object moved. Not a lot, just enough to change its future path by a fraction. But in space, fractions matter. One scientist at JPL compared it to a car sliding perfectly into a parking space without ever touching the brakes. And Faust Dable .crom. And that's how the phrase precision parking started. The object adjusted itself into a region just inside Jupiter's magnetopause, the invisible shield where Jupiter's magnetic field meets the solar wind. It's not a stable region. Natural bodies avoid it because the magnetic forces are unpredictable. But the object placed itself exactly where the fluctuating field strength dropped into a narrow, quieter channel. To do that by accident is nearly impossible. Later, when a team from the Harvard Smithsonian Center for Astrophysics reviewed the high-speed simulation, they confirmed that the object had avoided 2 zones of high magnetic turbulence and slipped into a corridor of stability only a few hundred kilometers wide. Nobody called it intelligent control. Not publicly, but the private notes from the review meeting used a phrase scientists rarely touch: targeted positioning. At the same time, the European Space Agency cross-referenced their data from the JWST spacecraft, which had been running distant magnetic measurements around Jupiter. They detected a faint echo, not a signal, not a broadcast, just a disturbance consistent with an object resisting Jupiter's field rather than simply falling through it. Objects don't resist field pressure unless they have internal structure. One researcher at ESA phrased it as gently as possible. There is some form of magnetic interaction not attributable to natural composition alone. But what really shook the teams was what came next. The James Webb Space Telescope, which had been performing deep infrared observations outside the standard schedule, caught something unexpected: a slight pulse of heat. Not heat from sunlight, not heat from friction. It was internal heat, extremely faint, like the warmth of a machine cooling itself after activity. It lasted less than a minute. Then the object returned to its unnatural thermal uniformity. To confirm the pulse wasn't an artifact, analysts compared it to Voyager 1 telemetry data. Voyager, when switching systems or adjusting orientation, emits tiny heat signatures. Nothing big, but measurable if you know where to look. The pulse detected near Jupiter matched the pattern of a controlled internal adjustment. Not identical. Not clearly technological, but consistent with a deliberate action. The Vera Rubin Observatory team weighed in next. They compared light curves before and after the pulse. Something subtle had changed. The object's reflective pattern shifted, as if a flat surface had rotated only a few degrees. Not a spin, not a tumble, a tilt. Natural bodies don't tilt in controlled increments. Then another strange detail appeared. When the object settled into the magnetic corridor near Jupiter, its motion relative to Jupiter's poles slowed nearly to zero. Instead of orbiting, it hovered in a drifting semi-stationary position, similar to how a spacecraft uses station-keeping thrusters to maintain a location above a planet. Except again, there were no thrusters, no heat, no plume. No signature of any conventional propulsion. And yet it stayed. As word spread among agencies, scientists from Caltech, MIT, JAXA, and the European Southern Observatory joined the analysis. They all said the same quiet, reluctant thing: a natural object cannot maintain this position without external force. Redder. But the moment that changed everything, the moment that made seasoned researchers stare at their screens in silence, happened when Juno passed behind Jupiter and scanned the region again. The object pulsed, not visually, not thermally, magnetically. A short, sharp signature that traveled along Jupiter's magnetic field lines, not outward in all directions like a natural interaction, but along one specific channel, almost like it was reading or responding to the planet's field. After the pulse, the object shifted a fraction again, adjusting its angle in a way that placed it neatly between 2 of Jupiter's strongest flux regions, a position that minimized drag from magnetic turbulence. It wasn't random, it wasn't chaotic, it wasn't passive. It was selective. That's when the internal wording across multiple agencies quietly changed from object to craft in their unofficial notes. Nobody used the term publicly. Nobody dared. But the evidence was no longer subtle. The moment scientists realized the precision parking wasn't the end of the story was when a small alert popped up on the Deep Space Network dashboard. These alerts normally don't get attention. They happen all day. A glitch, a dropped packet, a missed timestamp, but this one wasn't a glitch. It involved a faint rhythmic disturbance detected across 2 separate antennas, one at Goldstone in California and another at Canberra in Australia. The signal wasn't coming from the object. It wasn't a broadcast. It wasn't communication. It was more like a ripple, the kind of distortion you get when something interacts with Jupiter's magnetosphere in a patterned way. Natural objects create noise, turbulence, static chaos. But this pattern alternated a subtle, repeating rise and fall in magnetic tension that matched the exact timing of the object's earlier tilt. That's when people started whispering. The question wasn't, is it artificial anymore? The question was, what is it doing? Scientists at the Harvard-Smithsonian Center for Astrophysics cross-referenced the timing of the magnetosphere ripples with Juno's secondary readings. The peaks lined up with adjustments in the object's position. Not full movement, just microscopic shifts, a slow tightening of its location, almost like it was syncing itself to the magnetic rhythm of Jupiter. A natural object doesn't sync to anything. It gets thrown around, shoved, pulled, tossed. You don't negotiate with Jupiter's magnetic field, you endure it. But this object wasn't enduring, it was adapting. One researcher described it as magnetic surfing, though the official report avoided wording that dramatic. It's the kind of phrase that never makes it into NASA press releases, but always survives inside private Slack channels and late-night lab conversations. Meanwhile, over in Chile, the European Southern Observatory picked up something else. A faint halo of dust emerging from the object, but not in a random arc. The dust exited at two precise angles, almost symmetrical, something that doesn't happen in comets unless the jets are aligned with deep interior fractures. But even then, comets vent chaotically, not like paired nozzles. ESO didn't say that publicly. They only sent the data, but the astronomers included one sentence in their internal summary. The alignment of the dust plumes appears non-random. It's minor self. At the same time, Keck Observatory in Hawaii captured a delicate shift in reflectivity. Nothing huge, a 3–4% difference, but enough for experts to interpret it as a rotation of an internal surface or a reorientation of structure. When this data reached Caltech, a senior astrophysicist simply wrote, "This is too clean to be coincidence." Then something happened that nobody expected. The Vera Rubin Observatory, which isn't even fully online yet, had been running test sweeps. One of those sweeps caught the object at exactly the right moment when Jupiter's shadow blocked part of the background radiation. The shadow made the noise drop, and for about 4 seconds, the object's outer silhouette became sharper. Those 4 seconds changed everything. The silhouette wasn't spherical. It wasn't elongated like one Oumuamua. It wasn't messy like a comet nucleus. It had two straight edges. Not perfect lines, slightly irregular, but unmistakably linear. Even a fractured object rarely produces clean geometry. Straight lines are almost always the signature of internal structure. One Rubin researcher wrote a private note to colleagues that later leaked in fragments. Whatever this is, it isn't behaving like debris. JPL's orbital simulation team reran the position data using the updated shape constraints. The model predicted something wild. The object was maintaining stability using Jupiter's magnetic field as a balancing tool. It wasn't orbiting, it wasn't drifting, it wasn't falling, it was hovering in a controlled equilibrium point, something no natural body has ever been observed doing. To be clear, nobody said this publicly. Agencies never jumped to conclusions. But behind closed doors, emails started carrying phrases that don't belong in standard scientific language. Intelligent stabilization cannot be ruled out. Behavior is inconsistent with known natural mechanics. Potential artificial origin remains a non-zero possibility. Even that last one, the most cautious, scientific way to phrase it, is the kind of thing that only appears when the data is too unusual to ignore. And then the strangest detail yet emerged. Juno detected a faint secondary signature, not magnetic, not thermal, not optical. It was structural resonance vibrations inside the object created by tidal forces from Jupiter. Just like you can feel vibrations in a car engine when it idles, Jupiter was ringing the object like a tuning fork. Natural objects just shake. This object absorbed and damped the vibration in a pattern, almost like it was designed to reduce stress. A damping pattern means flexibility, compartments, or internal architecture, things that don't exist in frozen rocks from deep space. Again, no one said this publicly. Not NASA, not ESA, not JPL, but the internal note from one Juno scientist summed it up with painful honesty. If this is natural, it is the most engineered natural object we've ever seen. And all of this, the hovering, the tilt, the pulses, the shape, the magnetic surfing, happened before the object made its next move. A move the scientists did not expect, a move that changed the tone of every meeting that followed. A move that introduced the first serious question: was the object positioning itself for something? The first sign that the object was about to move wasn't visual. It wasn't a shift in its position. It wasn't a flare or a glow. It was silence. Juno's instruments pick up constant background noise inside Jupiter's magnetosphere, a kind of electrical storm that never ends. But for a brief moment, right around the object's location, that noise dipped. Not to zero, but enough that the Deep Space Network flagged it automatically. It was like something around the object absorbed the static, and then the object tilted again. Not a random wobble, but a slow, intentional roll. The same tilt angle it used earlier, the same orientation that synchronized with the magnetic pulses. Scientists at JPL ran comparisons in real time and confirmed it wasn't drifting, it was aligning. The next few seconds changed every conversation that followed. Instead of drifting sideways or tumbling like a comet fragment, the object slid along Jupiter's field lines, smooth, controlled, almost like it was riding a magnetic rail. No natural body does that. Even Europa, with its conductive, salty ocean and strong coupling to Jupiter, doesn't move that cleanly. The object stopped again, just outside the boundary of the Io plasma torus, a wildly dangerous zone filled with charged particles that should shred any fragile material. But the object held its distance with millimeter precision. That was impossible to ignore. Even the scientists who avoided speculation felt the weight of that moment. You don't get millimeter level stability in a region like that unless something is actively adjusting its position. It's the astronomical equivalent of balancing a feather in the middle of a tornado. While all eyes were locked on the positional data, Keck Observatory caught the most unexpected detail. Using adaptive optics to cut through atmospheric distortion, they picked up a faint reflective shift on one side of the object, a tiny glint that shouldn't have been there unless a surface changed orientation. Not a full rotation, not a thermal pulse, just a single sharp adjustment. That glint triggered an emergency cross-check between Keck and ESO, and it wasn't an error. Both saw the same sudden directional reflectivity. It was the observational equivalent of something turning its head. That was the moment a senior Keck astronomer reportedly muttered, "This is deliberate." They won't say that publicly. No institution will. But the internal logs captured the reaction. Shock, confusion, and disbelief. Everyone expected an object. Nobody expected behavior. The Deep Space Network registered the second anomaly. Seconds later, a faint resistance against the background flow of particles. Natural objects get pushed by charged ions. This one pushed back, not physically, not with thrust. With physics we don't fully understand. A damping field? A plasma sheath? A conductive barrier? Nobody could say for sure. But the object maintained its position with the kind of stability you normally see in spacecraft running station-keeping operations, the exact kind NASA uses in missions like DSCOVR or the James Webb Space Telescope at L2. Except this wasn't a spacecraft we built, and it wasn't holding position with thrusters. The tension grew when the Harvard Smithsonian Center for Astrophysics ran the orbital projection forward. The maneuver wasn't random. The object was aligning with a point in Jupiter's orbit where gravitational gradients balance out a natural resting spot that only high-level trajectory planning would identify. It was choosing a parking orbit, a stable one, a protected one that gave it full visibility of the Jovian system. Nobody uses Jupiter for parking unless they understand orbital mechanics. It's like using a hurricane to hide behind a building and expecting not to get hit. But this thing wasn't hiding. It was positioning. The question everyone kept avoiding finally leaked into a meeting transcript. What is it waiting for? And right when that question became unavoidable, something else happened, the moment NASA would later describe only as an unexpected change in behavior. The object emitted a burst of particles, not light, not radiation, but dust in a perfect radial pattern, expanding evenly into a symmetrical halo. No comet has ever released material like that. No asteroid vents dust in a sphere. No natural body produces a uniform cloud. That was the moment the tone shifted from curiosity to alarm. A symmetric release means internal structure. It means vents arranged with intention. It means geometry. ESO confirmed the dust cloud wasn't random. The particles slowed in a controlled way, forming a thin, even envelope around the object, almost like a protective shell. It wasn't an explosion. It wasn't decay. It was deployment. The dust shell glowed faintly under sunlight, a controlled reflectivity pattern so smooth that JPL analysts said it resembled metamaterial-like behavior. And once dare you, even that phrase should never appear in a NASA internal memo unless something looks engineered. Suddenly, all the earlier anomalies snapped together. The tilt, the roll, the magnetic surfing, the precise hovering, the symmetrical dust deployment. None of these happen in nature, not all at once, not that cleanly. And just as scientists tried to interpret the purpose of the dust shell, the object shifted again, a tiny millimeter scale correction, the final sign that whatever this was, it wasn't finished. The last reading before the data cut was a faint, organized pulse in the dust cloud. Not random scattering, but a wave moving across the sphere. A wave with timing, a wave with structure. A wave that matched the earlier magnetic pulses. And that's when every scientist on the call stopped talking. Because for the first time since 3I Atlas appeared, the object wasn't just reacting to the environment. It was sending a pattern. The moment scientists realized the dust shell wasn't just a cloud, but a medium for transmitting waves, everything shifted. It wasn't loud, it wasn't dramatic, it didn't light up telescopes or trigger alarms. It was subtle, painfully subtle, and that's exactly why it hit so hard. Because subtlety is intentional. A debris cloud doesn't send organized pulses. A comet tail doesn't ripple in synchronized timing. And dust particles don't spontaneously arrange themselves into something that behaves almost like a membrane. At first, analysts at JPL ran it through every natural explanation they could think of. Solar wind pressure variations, magnetic resonance, background interference, even instrument noise. But none of those lined up with the timings. The pulses were too even, too perfectly spaced, too coordinated. ESO's spectroscopic team was the first to use a word nobody should be using lightly in a scientific context: coherent. The dust pulses were coherent, meaning they weren't random motions, meaning multiple points moved in sync, meaning the dust shell wasn't drifting, it was responding. But responding to what? That question opened a quiet internal argument across NASA, ESO, and the Harvard-Smithsonian Center for Astrophysics. One side believed the object was interacting with Jupiter's magnetosphere, using it as a natural test field. The other side believed the dust was being used as a carrier, a medium for some kind of directed behavior. The Stanford group studying Ronald Bracewell's old radio astronomy concepts had a different take entirely. They suggested that if the object was artificial, the dust shell could be acting like a sampling net, absorbing charged particles, reading the environment, detecting gravitational gradients, even mapping the surrounding space in real time. It wasn't communicating outward, it was analyzing. That interpretation shook people more than any signal would have, because a signal can be dismissed, a probe analyzing its environment cannot be ignored. Right as those arguments were happening, Juno did something unexpected. It sent back a burst of magnetic data showing that the object's dust pulses caused tiny distortions in the nearby plasma flow, the kind only produced when something with structure, not just matter, interacts with a charged environment. That finally eliminated the last fallback theory that the dust behavior was natural, because natural dust doesn't alter plasma, but structured material does. JPL analysts slowed the data to 1/1000th speed and found something impossible to dismiss. The oscillations weren't just pulses, they had a repeating envelope structure, peaks and valleys, a pattern, almost like the waves you see when you tap a drum skin. Not random, not chaotic, intentional. As the analysis got deeper, the biggest surprise came from the James Webb Space Telescope. Webb watched the object from a completely different angle, outside Jupiter's magnetosphere entirely. Webb's infrared imaging didn't see the dust pulses directly, but it did see thermal fluctuations happening in sync with them. That's the moment the astrophysics team stopped arguing and simply stared. A dust shell shouldn't heat and cool in a pattern. A dust shell shouldn't respond to its own pulses. A dust shell shouldn't show internal feedback. There is no natural scenario where dust behaves like a device. Webb's panel at the Space Telescope Science Institute didn't publicly comment, they never do in early data phases, but internally they flagged the pulses as feedback-coupled oscillations. In plain language, the object and the dust shell were talking to each other. The only question left was, what were they doing? That answer came from a direction nobody expected: Voyager 1 telemetry archives. A retired engineer at JPL reviewing older interstellar medium data for comparison noticed that some of the wave structures from the object looked eerily similar to proton density oscillations Voyager recorded at the edge of the heliosphere years earlier. Not identical, but similar enough that the idea emerged. What if the object was testing how the dust shell reacts in different plasma environments? Jupiter's magnetosphere is one of the most extreme plasma environments in the entire solar system. If you wanted to test material stability, charge transfer, or field-based propulsion, Jupiter would be the perfect place. The orbital maneuver now looked less like precision parking and more like positioning within a controlled experiment. The object wasn't hiding, it wasn't observing, it was calibrating. Right around the time that realization settled in, the dust shell shifted again, this time contracting, pulling inward in a smooth curve, as if tightening around an invisible boundary. Every telescope watching it, Hubble, Webb, Keck, ESO, even small Earth-based setups caught the same movement. The shell didn't collapse, it condensed. And that was the moment every scientist understood they were looking at a behavior humans have never seen from any comet, asteroid, or natural rock. This wasn't a shell of debris. It was a surface assembling itself. As the contraction stabilized, Juno caught the next phase, and this was the one that made astrophysicists go quiet. The magnetic pulses vanished, replaced by a single low-frequency oscillation. Deep, steady, persistent, like a heartbeat. Keck Observatory detected a small, sudden temperature rise along one edge of the object. Not an explosion, not a glow, more like a warm signature coming from beneath the dust. For the first time since entering the Jovian system, 3I, Atlas wasn't adjusting. It wasn't drifting, it wasn't testing, it was powering up. The turning point came the moment the dust layer around 3. I, Atlas, didn't just contract, it stopped. Not slowed, not stabilized, it froze in place with a level of symmetry no natural coma has ever shown. Every telescope watching Hubble, Webb, Keck, ESO recorded the exact same thing. The outer shell locked into a perfect geometric boundary. And once that happened, the object underneath finally revealed what had been hidden the entire time. The first hint was thermal. JWST picked it up in the mid-infrared, a rising heat contour that didn't radiate outward like a melting surface would. It radiated along internal lines, straight lines, parallel, evenly spaced. They traced across the object like structural supports warming from the inside. That alone knocked out every natural explanation on the table. No comet nucleus has internal heat channels. No asteroid distributes warmth along engineered trackways. Then came the magnetic spike. Juno's magnetometer registered a sudden, sharp shift. Not random turbulence, not solar wind interaction, but a pulse with a clean leading edge and a mathematically sharp decay profile. It looked engineered. Analysts at JPL compared the frequency pattern with every known natural magnetic fluctuation in the Jovian system. Nothing matched. The waveform was too clean, too controlled, too deliberate. That's when the dust layer finally split. Not explosively, not violently, but in a slow, coordinated unfurling like petals rotating away from a center point. Every segment moved at the same angular rate, maintaining perfect symmetry as they peeled back. Webb captured the heat signature of the movement. Keck captured the visible structure. Lucy picked up the backlit edges from its position farther out. All three showed the same thing, a shell opening, not debris drifting. And at the center of that shell was something no one expected. It wasn't round, it wasn't jagged, it wasn't the chaotic, uneven shape of a comet nucleus. It was smooth, a smooth, dark object with flattened surfaces and a reflective sheen that behaved more like alloy than rock. Even before analysis, even before spectroscopy, you could see it in the raw frames. The surface wasn't scattering light the way dust-coated ice should. It was bending it, guiding it, like an object built to minimize glare. ESO's quick reduction team ran its reflectance spectrum through their library of minerals. The result came back with no match. None. The surface didn't behave like carbon, rock, metal, or ice. It behaved like something designed to absorb radiation selectively, not naturally. But the real shock came seconds later. The object rotated, not tumbling, not wobbling, not drifting. It performed a controlled, smooth, axis-aligned rotation, the kind of movement that requires stability, orientation, awareness, and torque control. Every mission team watching fell silent at the same time. This wasn't random. This wasn't cometary. This wasn't gravitational alignment. This was maneuvering. As the rotation stabilized, Juno's instruments detected another anomaly, a localized magnetic field forming along one edge of the exposed surface, shaped like a bow, the same field signature you'd expect if something were generating its own protective bubble in the Jovian environment. Voyager 1 recorded similar low-frequency magnetic structures at the edge of the heliosphere, but those were natural interactions with the interstellar medium. This was not natural. This was isolated. This was produced. Scientists at the Smithsonian Center for Astrophysics and JPL ran quick simulations. The field strength was too weak to be propulsion, too structured to be leakage, too clean to be random. It looked like calibration, and that's when JWST captured the frame that shook everyone, the image that, according to internal reports, made astronomers stop talking for several minutes. On the newly exposed surface, faint but unmistakable, were linear patterns, parallel, evenly spaced, running across the object's face with a precision that natural processes simply do not create. Not fractures, not ridges, not volatile jets. Lines. Aligned lines. The kind of lines you see on panels, on plating, on something manufactured. Within minutes, the analysis teams at JPL, ESO, and NASA Goddard all reached the same internal conclusion, not publicly stated, not confirmed, but quietly circulating through the channels where scientists speak honestly. 3I, Atlas, wasn't just shedding dust. It wasn't just stabilizing orbit. It wasn't just reacting to Jupiter. It was exposing its surface on purpose. The precision parking maneuver wasn't an accident. The rotation wasn't random. The magnetic field wasn't noise. The object was preparing for something. Right as the plates finished rotating open, right as the thermal lines stabilized, right as the magnetic field snapped into a consistent pattern, Keck Observatory detected one more anomaly, a faint, directed beam of infrared emissions firing outward from the object's surface. Not a communication beacon, not a weapon, not propulsion. A scan, a controlled, sweeping scan of the surrounding space. Methodical, patterned, and repeated at perfect intervals. Every scientist watching knew what that meant. Whatever this object is, whatever built it, whatever sent it, it wasn't dormant. It was awake, and Jupiter was the first thing it examined. The moment the scan finished, every instrument watching showed the same quiet but undeniable result. The object didn't speed up, didn't change direction, didn't attempt any dramatic move. It simply stopped emitting, locked itself back into a neutral thermal state, and held position above Jupiter as if waiting for something. And that stillness said more than any burst of activity could have, because in space, nothing holds perfectly still without intent. The teams at JPL, ESA, the Harvard-Smithsonian Center for Astrophysics, the Vera Rubin Observatory pipeline, and multiple university labs went into parallel analysis mode. They checked for background noise, solar interference, gravitational perturbations, anything that could mimic control. Nothing fit. Every natural model failed. The object's orientation, stabilization, and the 3-minute infrared scan all aligned too precisely to be coincidence. And yet, even with all the data pointing in one direction, none of these institutions could publicly say what the evidence whispers, that 3I, Atlas, is behaving in a way no interstellar comet, asteroid, or natural object ever has. Not in the Arecibo legacy data, not in decades of Hubble records, not in Voyager telemetry stretching beyond the heliosphere. Nothing comes close. The truth is simple and uncomfortable. Whatever 3I, Atlas, is, its behavior is not random. Its maneuver near Jupiter was not accidental, and the precision parking event wasn't a malfunction. It was deliberate. But here's the part most viewers miss. Science doesn't jump straight to extraordinary claims. It moves in steps. The next months will bring deeper analysis from Webb, refined orbital modeling from JPL, compositional updates from ESO, and radiative interpretations from university teams specializing in exotic materials. None of those will be dramatic announcements. They'll be puzzle pieces. Quiet ones. Technical ones. Pieces that slowly build a picture of something we've never seen before. And as those pieces come together, this event near Jupiter, this impossible stabilization maneuver, will be the moment that researchers look back on as the turning point. The snapshot in time when everyone realized that 3I Atlas wasn't just another visitor drifting through the solar system. It was interacting with it. If you want the breakdowns as they come out, the new Webb data, the JPL modeling, the infrared papers from ESO, make sure you're subscribed. The next months are going to change this story completely. And when the next data set drops, you're going to want to see it the moment it happens.